It surrounds us, in the cars we drive, in the buildings where we work, in the multitude of products we depend on every day. It protects our possessions and entire nations. It packages our food and our appliances. For nearly a century, steel has fueled the fire of an industrial revolution. In the process, it has created communities, livelihoods, lifestyles. Each year, the free world consumes nearly 800 million tons of steel. The United States alone requires 1/8 of that amount. Steel is a manufactured product, born of fire and human effort. But it also is a gift of the earth. It takes iron ore to make steel, and it takes engineers and miners with the help of massive earth-moving machines to unlock those vaults and exploit the vital riches within. For over 3 decades, the Iron Ore Company of Canada has maintained a position of prominence among the iron ore producers of the world. The largest iron ore producer in North America, IOC ships its products throughout the globe to help feed the world's hunger for iron and steel. IOC's main mining and processing facility is located near Labrador City in the province of Newfoundland, Canada, where the summers are short and winter temperatures can fall to 40 degrees below 0 centigrade. Here, the company can produce up to 20 million tons of refined iron ore products a year. IOC owns a major interprovincial railroad, the Quebec North Shore and Labrador Railway, which serves both as a shipping line for iron ore cargo and as a lifeline to the communities of western Labrador. At the other end of the railroad, in the port town of Sept-Îles, Quebec, IOC operates one of the largest bulk shipping terminals on the continent. From here, IOC's products are shipped throughout North America and to distant ports of Europe and the Far East. It's an impressive company with an even more impressive history. Since Leif Erikson first landed on the shores of North America 1,000 years ago, the subarctic forests of northern Quebec and Labrador went largely unexplored. But by the 1930s, interest began to grow in the region's potential mineral resources. Of special interest to the United States steel industry was iron ore, because the natural iron ore deposits in the United States were becoming depleted after over half a century of mining. By the 1940s, as the winds of war swept around the globe and the need for weapons and armor heightened, exploration activity increased, resulting in the discovery of over 400 million tons of iron ore reserves near Knob Lake in the northern reaches of Quebec and Labrador. But exploiting the deposits presented many obstacles. One was how to retrieve and ship the iron ore from an undeveloped land 40% covered by lakes and marshes that experienced some of the harshest winter weather known to man. Another was how to finance such a project, which would require the construction of massive mining and processing facilities, power plants, and an entire infrastructure of town sites and transportation systems. In 1949, a consortium of U.S. and Canadian companies, led by the M.A. Hanna Company, a major independent iron ore producer, and including several leading steel producers, agreed to pool their resources and develop the project. The Iron Ore Company of Canada was formed. Thus began a 4-year construction project that would rival all that preceded in terms of size, risk, and cost. Ore in '54 became the rallying cry, as nearly 7,000 geologists, engineers, and laborers spread out to tame the vast wilderness. Among the most formidable tasks was the construction of a 580-kilometer railway stretching from the then small fishing village of Sept-Îles on the Gulf of St. Lawrence to Knob Lake. Surveying crews traveled by canoes in summer and dog sleds in winter. a weekly mail drop, their only contact with the outside world. Virtually all of the construction materials, from railroad ties to bricks and mortar, had to be shipped to the construction sites. The largest civilian airlift in history up to that time was organized to move materials, men, and machinery north. In just 4 years, IOC completed its railway, built town sites, including hydroelectric power plants near Sept-Îles and at Schefferville, Quebec, near the mine site, constructed a bulk ship-loading terminal at Sept-Îles, and built a major mining operation, complete with processing plants, loading facilities, and equipment maintenance operations. On July 15, 1954, the first shipment of iron ore left Schefferville on the newly built Quebec North Shore and Labrador Railway. IOC had met its goal of shipping ore in '54. In turn, it had created entire communities in a previously undeveloped land. It also provided the impetus for the construction of the St. Lawrence Seaway, which was built in part to provide an economical means of transporting Canada's iron ore to the steel mills of the Midwestern United States. Before long, IOC embarked on a series of expansion moves to meet an ever-increasing demand for iron ore. In 1959, construction began on the Carroll project near Wabush Lake in Labrador. The project involved construction of a mine, concentrating plant, and pelletizing facility, as well as the current town of Labrador City. In 1968, construction began on a new dock facility at Sept-Îles, big enough to load the largest ocean-going vessels. By 1970, increasing demand required the expansion of the Carroll project and the construction of iron ore processing facilities in Sept-Îles, which had grown from a small fishing village into a thriving cosmopolitan community with one of the highest per capita incomes in all of Canada. And in 1979, IOC, by now the largest iron ore producer in North America, shipped nearly 28 million tons of iron ore products. That would prove to be the company's all-time record, as the 1980s brought recession and restructuring to the global steel industry. Facing reduced demand from a shrinking North American steel industry and intense competition from overseas iron ore producers, IOC was forced to restructure its operations and look to new markets for its products. Once largely a captive supplier to its steel company owners, IOC had to realign its marketing and operations to serve the highly competitive global marketplace. Today, IOC is a cost-competitive, customer-driven producer of superior quality iron ore pellets and iron ore concentrates. M.A. Hanna Company serves as IOC's managing and sales agent. At the Carroll facility, IOC can produce about 10.5 million tons of iron ore pellets annually, which are sold to steel producers in North America and Europe. It also can produce an additional 8 million to 10 million tons of iron ore concentrates for sale in Europe and the Far East to be converted into sinter, which is used like pellets in the blast furnace. The production process begins in one of two open-pit mines at the Carroll project. The ore body is a hard specular hematite and magnetite iron formation that must be drilled and blasted with high-power explosives. Then dug from the ground by huge 10 and 13 cubic meter electric shovels. The ore is loaded into giant 150-ton diesel-electric trucks that are dispatched using a sophisticated computer system. The trucks, which cost over $1 million each, haul the chunks of ore to a fully automatic electric train for a 16-kilometer trip to the crusher, which can handle 2 train cars simultaneously. The next stop for the crushed ore is the concentrating facility, where it is upgraded from a natural iron content of about 39% to an iron content of about 66%. At the concentrator, the ore is ground in giant grinding mills into a wet slurry. Then the heavy mineral particles are separated from the light waste rock in a separation process that uses the forces of gravity, centrifugal action, and magnetism. The refined iron ore is then filtered and either shipped to market as iron ore concentrates or conveyed to the pelletizing plant to be processed into iron ore pellets. In the pellet plant, the concentrates are reground to a finer texture, then conveyed into giant balling drums to be converted into small 3/8-inch spheres called green balls. The green balls travel to the indurating furnace, where they are hardened at nearly 1,200 degrees centigrade into finished pellets. To satisfy varying customer needs, IOC produces two types of pellets, the standard acid pellet and a self-fluxing pellet containing dolomite and limestone, which enhance the steel-making process. IOC goes to great extremes to ensure that product quality is consistent and high. Both the concentrator and the pellet plant are monitored by sophisticated computerized central control rooms that continuously regulate the processing equipment. IOC also employs statistical process controls throughout the production process to ensure consistent product quality. From the Carroll project, the finished concentrates and pellets are shipped on the Quebec North Shore and Labrador Railway to Sept-Îles. It takes about 12 hours to make the 385-kilometer trip through the scenic wilderness. The iron ore trains can be as much as 250 cars long, and an average of 1.5 trains a day make the trip to Sept-Îles. The railway, which also serves as a common carrier, hauls about 18 million tons of cargo annually. At Sept-Îles, the iron ore is unloaded at a rate of 2 cars every 75 seconds. It is then stockpiled to await loading on bulk ore carriers. IOC's 267-meter-long loading dock can berth 250,000-ton ocean-class bulk carriers and holds the single shipment loading record in North America. But the secret of IOC's success extends beyond the company's sophisticated technology, beyond the hundreds of millions of dollars of invested capital, and beyond the wealth of available iron ore. The secret of IOC's success is the strength of the people who so effectively utilize these assets to produce a price and quality competitive product. Few companies can boast of a more skilled and dedicated workforce. Indeed, the same determination and talent that carved IOC out of the wilderness 4 decades ago is today pushing the company forward to meet the demands of the global steel industry. The products of their labor extend to the steel mills of North America, Europe, Japan, and Korea. The testimony to their talent is present in the cars we drive, in the buildings where we work, in the multitude of products we depend on every day. The Iron Ore Company of Canada, customer-driven, quality-conscious, and always in the forefront.
Forbidding north, but over the years one thing became clear. Lost behind these ranges, behind barriers of time and distance, of terrain and isolation, were enormous quantities of minerals, especially iron ore. How these riches were freed for use by man is our story. The drive for ore started at Sept-Îles on the north shore of the Gulf of St. Lawrence. Montreal is 484 air miles away. Montjoly, the nearest railroad point, is 141 air miles away. The ore bodies themselves are far to the north around Knob Lake. Builders pushed a 357-mile railroad north from Sept-Îles to reach them. A completely new town, Schefferville, was built to serve the mining area. Come back now to Sept-Îles as it was before the tidal wave of history washed over it and changed the face of the north. The centuries had gone peacefully for Sept-Îles with little change since Jacques Cartier had wintered nearby some 400 years before. The restless surf still beat across the bay he knew, unmarred by man, unchanged by time. It was a place of fishermen, trappers, and traders, perched on the remote rim of a little-known part of North America. But that changed at the midpoint of this century of destiny. The first agents of change were bulldozers, the cumbersome surgeons of industry, who reshaped the face of nature to fit man's needs. On October 2nd, 1950, they came ashore from a small coastal steamer and started knocking down brush back of the old village. They cleared the way for an army of men and materials soon to follow. A new kind of cloud formed in the untroubled St. Lawrence sky as steam-powered pile drivers hammered down corrosion-resistant steel from Sault Ste. Marie to transform a wilderness beach into a modern dock. Soon, 45,000-ton ore carriers would replace fishing dories along the Sept-Îles waterfront. Out in Sept-Îles Bay, a dredge pumped up thousands of tons of sand and water and pushed them into the area behind the new dock. The builders were making land here, building a firm base for a development of historic importance. But even from the first days of construction, they paid penalties of distance and isolation. The Gulf of St. Lawrence was the construction crew's highway to the world. All heavy equipment had to come over it. In calm weather, when they were lucky, in foul weather when they weren't, they shipped in a steady stream of massive equipment to carve a way through the wilderness and start iron ore rolling south. Winter as well as summer, the transports delivered what was needed. What they sent ashore reads like a capsule history of construction. Ore cars for the railroad fighting north. Locomotives to pull men and supplies up the line. Tractors to clear the way for construction. Trucks for the new roads now being built. Tank cars for the oil that powered the project. Ponderous giants to move earth and haul ore. Flat cars for northbound supply trains. Aggregate for concrete needed by a $250 million construction job. 4 contracting firms combined to handle the undertaking: Cartier, McNamara, Mannix, and Morrison Knudsen of Canada Limited. Iron Ore Company of Canada, which built the project, is owned by Hollinger Consolidated Gold Mines Limited, M.A. Hanna Company, and 5 steel companies: Armco, National, Republic, Wheeling, and Youngstown Sheet and Tube. They advanced $115 million of the $260 million total cost. The rest was loaned by 19 Canadian and American insurance companies. Harnessing the energy of the rushing Marguerite River was a vital link in the chain of construction projects that would transform the Sept-Îles area into a modern, integrated loading terminal, harbor, and town site. Here at Falls number 63, on the river's turbulent course down off the Laurentian uplands, builders began by quarrying local rock. They hauled it to a plant they built nearby, then crushed, washed, sorted, and sized it to process it on the spot into high-quality aggregate. This they used to make concrete, 52,000 cubic yards of it, to put a plug across the gorge of the Marguerite and capture the energy stored in the waters of a lake 53 miles long, diverting it to useful work in moving iron ore out to the furnaces of the free world. This was a project where everything had to be done at once to meet the need for ore. While some men labored on the Marguerite, others had already pushed steel north and were steadily sending supply trains along it up to the head of the rail, moving in men and material at an ever-increasing tempo, preparing to wage one of the epic battles of all construction history. They were breaking down the grim, guardian barriers of the Old North, pushing ahead with the steel rails and diesel might of the Quebec, North Shore, and Labrador Railway, the railway that would pierce the defenses of the North and open the wasteland to civilization. But no one challenges the North without paying the North's bitter price. At mile 12, a solid Laurentian cliff, half a mile thick, had to be tunneled through. And on the other side waited the gorge of the Moise River, 150 feet straight down a plunging cliff face. So construction men lifted themselves by their own bootstraps and built a bridge from the air. A helicopter carried a light line across to the far side of the gorge. That made it possible to send across a chair and men coasting out over infinity. The single cable became a web, supporting men and steel farther and farther out over the rushing river. Fighting for every inch they made, construction crews drove to complete the 705-foot span that hurdled one of the major barriers on the way north. They bridged the Moise in June 1952, but the bridge led into rock. Mile after grim, forbidding mile of it, rising in sheer canyon walls. Before there could ever be ore rolling down to market, there had to be men climbing up, sweating their painful way across the face of the bleak rock, clinging like flies to the harsh cliffsides along the Moise River. Fighting drill bits and stern faces reflect the nature of the struggle. Between mile 12 and mile 17, road builders blasted down 1 million cubic yards of rock. And they built themselves a roadbed. 1 million yards of rock and 600 tons of dynamite, and they cleared a way for the trains to keep moving north over the new rail, rolling toward the head of steel, toward the wilderness they had not yet breached. Northbound trains pounded through the new tunnels and across the freshly laid rail with more supplies and yet more equipment for the next stage of the job. They supplied the 18 major construction camps along a right-of-way stretching farther than from Hamilton to Montreal, and supported 6,900 men, most of them from Quebec and Newfoundland, who labored here at the construction peak. And always the trains drove north, toward the head of rail, toward the new problems the hostile countryside presented. Water was the headache after rock had been conquered. The central Labrador Plateau is a place of many streams, many lakes. 19 bridges and trestles carry the railroad north. Trestles were often built of local lumber and erected with improvised pile drivers, as builders learned to use the country's own resources to meet its challenges. And where there is water in the north, there is often muskeg, a hopeless ooze of partially decayed vegetation accumulated over slow centuries. Movement through or across it is difficult in the extreme. Luckily, the route picked for the Quebec, North Shore, and Labrador went across muskeg averaging 3 to 4 feet deep, not the bottomless kind found elsewhere. When drainage was established, track builders went right over it, knowing it would compress gradually into a stable roadbed. Many techniques speeded steel north. Ties, 1.5 million of them, were distributed one shift ahead of the track-laying crews. A crane moved out to the very end of steel, dragging behind it a skeleton car loaded with 132-pound rail made in Nova Scotia, the heaviest ever rolled in Canada. Every 60 seconds, the crane would swing a rail out to the waiting crew, which had long ago reduced the procedure to a fine art. As soon as the new track was bolted and spiked, the crane would move forward and repeat the operation. When all the rails had been taken from a car, it was disassembled and lifted off the track. More rail was moved into place, and the crew pushed on. And wire went north with the rails, 355 miles of it, shining strands for the communication system that would tie the project together. The long ore trains soon to come would be guided by a centralized traffic control system. A dispatcher scores of miles away would have the railroad at his fingertips, controlling it with signals and automatic switches. In a land where you must fight for every foot you gain, there had to be lots of new answers to transportation problems. Helicopters leapfrogged up the line, reaching points otherwise inaccessible. Experimental swamp buggies were tried to lick the problem of muskeg. Pointers carried survey teams deep into the bush. Project-built boats freighted 150,000 tons across the lake region. Snowmobiles helped conquer the problems of winter in the backcountry, and there was a constant struggle to keep the vital railroad open to the construction area. Convoys of great trucks fought their way north for 10 weeks across the frozen lakes and swamps during 2 winters, burdened with heavy equipment and supplies for spring work up the line. The story that made history was written in the sky. The saga of the Hollinger-Ungava Transport Company. Always overhead was the sound of a plane, and the drone of steady motors was a constant accompaniment to the drive for ore. Winter and summer, and around the clock, a plane was taking off or landing somewhere from Montreal to Montjoly to Sept-Îles to Knob Lake. And this in the face of some of the world's worst flying weather. Everything that moved up the line had to go at least part of the way by air. This was the largest civilian airlift in history. It literally flew the Quebec North Shore and Labrador Railway into existence. Ground crews could service a plane and have it ready to make the next trip in its tireless circle in as little as 15 minutes. A constant stream of men and material moved by air to speed the day ore would be rolling out of the north. Knob Lake, there was always wilderness under the wing. Hollinger-Ungava carried nearly 139,000 passengers and 170 million pounds of air freight, totaling nearly 15 million ton miles, and all without scratching a crewman or a passenger. The airline missed only 11 operating days. There were 14 landing strips up the line, many of them. Crosswind landing gear enabled aircraft to use them in spite of the hazard of tricky cross currents swirling through the deep valleys. The story at Menehek sums up HUT's triumphs. At Menehek Rapids, the airline flew in 7,000 gallons of gasoline a day and 190,000 bags of cement to build a 517-foot dam. And at Menehek, the North struck back savagely. A temporary cofferdam and bridge washed out in the spring of 1952, destroying months of effort. Throughout the wilderness, data on stream flow, runoff, and other information engineers take for granted in more gentle lands was completely missing. The nature of the violent North was an inescapable and unpredictable factor in all calculations. But with a persistence as overpowering as the machines they used, construction crews carved themselves out a place to stand on the water-soaked silt. At Menehek, the central concrete structure is flanked by an earth dam 3 miles long. Once again, local rock furnished aggregate. It was crushed and washed to make a suitable building material for the severe demands it would have to meet. Mixed with the 190,000 bags of cement the airlift flew in and used to make concrete. 31,000 cubic yards of it to dam the rapids and defy the springtime ice. The fury of the spring runoff would now turn generators to power mining operations, and the back of the dam itself became a bridge to carry the lengthening railroad north to the ore bodies. Now supply trains were moving steadily into the perpetual twilight of the subarctic winter as Sept-Îles became a staging area for a last massive push up the line. It was the winter of 1953-54. In just a few months, the first shovels had to be working in ore. Builders moved up tough and able men who drove ahead for 10 and 12 hours a day in 50 below zero weather. Machines are strained to the utmost under these conditions. Some operate at only 50% efficiency. Engines that stop can be started only with great difficulty, but the men were invincible. In December 1953, track-laying crews made more than 2 miles a day for 10 days. Many of the 440 miles of rail on the project were laid under conditions like these. It was 56 below on the morning of February 13, 1954. Those R. Timmons of Hollinger Consolidated Gold Mines drove the Golden Spike, symbolizing the end of rail construction, although it did warm up to a balmy 20 below for the ceremonies. And all during the time construction crews were driving rail north, other men had been working in the ore country itself. Burnt Creek, now the site of a large mine, was the first settlement. Exploration drilling was based here. Drill crews sank more than 250,000 feet of drill holes and proved 417 million long tons of direct shipping iron ore, revealing the promise of the North. Nearby Knob Lake, now supplanted by the new town of Shefferville, was the seaplane base. Float planes working out of this area ranged far across the interior, supplying prospectors and geologists engaged in a search for new deposits that continues to this day. These men in their crude camps were the first heralds of a new age, bringing a new urgency to the unhurried North. Once they came and saw and reported, nothing could be the same. Change moved into an unchanging land. Steelwork began to rise against gray-green hills. On one side of an ancient valley, civilization. On the other, the timeless North. Men began to move across the dreary face of a land so forbidding even the caribou had left it. Soft touches appeared even in the hard North. And suddenly, over the hill is a town, bustling, alive, an outpost on the doorstep of the Arctic with great promise for future development of much of a new Canadian frontier. A town with construction of all kinds going on. The original mining activity has encouraged other building. Now that the railroad has tied the North to the world of men, Shefferville is the center for activities throughout a vast hinterland. 2,500 persons live here now, and more are coming. Not to the barren subarctic that hasn't changed since the last glacier, but to a modern town with green lawns, where children run across a churchyard. And back of it all is the thing that brought us here. Iron ore, the prime resource of our age. Ore of a quality furnace masters haven't seen for a generation. Present in enormous quantities along the weathered bridges where Quebec and Labrador meet and run together. This is what we came for, what we fought the North for, dug and blasted and drag-lined our way across the face of a remote and hostile land to get. This is a resource the free world badly needs, and we could no longer allow the North to keep it hidden and forbidden to men. Already the shovels are turning hillsides into deep pits, taking bites of 6 to 8 cubic yards every time they nod their heads, and every bite is another assurance that North America will continue to have the raw materials it needs. In the mining season of roughly 6.5 months, these pits can produce between 12 and 15 million tons of iron ore. This from the heart of a barren subarctic wilderness. An ultimate production of more than 20 million tons is possible. After they leave the shovels, trucks labor across the ever-deepening pits toward railroad bins that rise starkly against the horizon. This is high-grade, direct shipping ore. It needs no concentration, but as trucks dump it, the ore is screened and crushed to maintain a relatively uniform size. Then it's conveyed to the top of bins sitting astride railroad spurs. Empty cars roll underneath to receive as much as 85 long tons of ore. The whole mining region, centering around the now abandoned settlement of Burnt Creek, is laced with spurs that lead back to a central yard, Silver Lake, where trains are made up for the long trip south. There, cars are sampled. Iron ore is a natural product, and like all natural products, it varies. Samples are taken to make sure that a furnace master thousands of miles away gets just the blend he specified. Then the long trains move south. freighted with promise. Each represents $2.5 million worth of rolling stock, carrying down the ore needed to supplement traditional iron ore sources so that North America's growth can continue unhampered, and needed also to help the recovery and expansion of Western European economies, which are rapidly outgrowing sources they relied on in generations past. Iron ore from the north is helping build the future throughout the free world. Steadily, the long trains roll down to Tidewater, and all down the line, we're ready for them. Ready at Menahek, where the springtime ice crumples harmlessly, while as much as 100,000 tons of ore a day roll past. And the fury of the rushing water spends itself in turbines that generate 12,000 horsepower, used to dig out ore and start it south. Ready at Marguerite, where falling water, idle since before the dawn of history, has been put to work as electric muscles move ore on the last stages of its long journey from the north into the holds of a fleet of deep-water ore carriers. The harnessed fury of the falls turns two 12,500 horsepower generators which supply the needs of the terminal and dock area. They push 44,000 volts up over the hill and around the bay to Sept-Îles, where it powers a large-scale shiploading and harbor operation. Here, a triumph of 20th century industrial pioneering has changed a fishing village into a name familiar to seafaring men the world over. And we're ready here, too, ready with a vast net of facilities where once there was only black spruce and sand. The iron ore terminal area back of the docks receives as many as 10 trains a day, rolling in from the iron country to the north. They are broken up at the far end of the receiving yard as a gentle shove from a locomotive starts cars rolling down grade from a high point known as a hump. Ponderous, unhurried, but always on the move, the cars add up to a force as irresistible as a river rising slowly to flood, a flood of new ore for the hungry furnaces. Gravity keeps the cars rolling while an operator in the tower controls their speed and switches them on to any of 12 classification tracks, depending on their analysis of ore. Ore of many kinds and grades can be blended to provide a ship's cargo tailored to the consumer's specifications. Then a sidearm pusher cuts out cars like a dog takes sheep from a flock and starts them toward the dumper. A cable-driven Barney pushes them into the tandem rotary dumper that can turn over and empty 2 cars every 67 seconds. Finally, empty cars circle away after they've been dumped. In less than 72 hours, they'll be back in Sept-Îles with another load. The ore they have just given up is conveyed to mixing bins and then sent out over a network of belts either to stockpile or to a waiting ore carrier. These belts can move ore along at a peak rate of 8,000 tons an hour, pouring it into the holds of ships that call from every great ore receiving port washed by the Atlantic and the North Sea. Booms on the loading towers are movable, so they can evenly distribute their heavy cargo, keeping the ship in trim. This is the ore that will enter the lives of millions, in forms as varied as jet aircraft, bulldozers, and paring knives. We live in a world built of steel, by steel, and with steel. And steel production depends on having iron ore available when you need it, where you need it, and in the quantities you need. As many as a dozen ships a day clear from Sept-Îles during the peak of the shipping season, with cargoes destined for great steel-making centers all over 2 continents. Large shipments move from Sept-Îles to East Coast ports such as Philadelphia and Baltimore. Other ships clear for Rotterdam and other European ports. Hamilton, Cleveland, Ashtabula, and similar Great Lakes ports will receive direct shipments in large vessels when the St. Lawrence Seaway is completed. Until seaway completion, however, much ore is shipped to Contrecoeur up the St. Lawrence 25 miles from Montreal. Here, as part of the overall Quebec-Labrador project, we built an integrated transshipment point. Ships from Sept-Îles, some of them in a regular shuttle service, bring in as much as 30,000 tons of ore at a time. Since these giant carriers cannot get past the St. Lawrence Rapids, they are unloaded here. Their ore can be stockpiled for later transshipment, or it can go directly to the mills by one of two ways. When overland haulage proves the most desirable method, ore is shipped by rail to the traditional steel centers of the American Midwest. The conveyors can be fed either from stockpile or directly from a ship under the unloading tower. Ore can also be fed into small freighters that can navigate existing St. Lawrence channels into the Great Lakes to reach other markets and consumers. But wherever and however it moves, the tumbling cascade of ore marks the defeat of the Old North. This vast, remote, and lonely land we found has changed now for the first time since the glaciers left it. The land God gave to Cain, as the first explorers called it, has been reclaimed for human use. Years of effort, thousands of men, $250 million, and the challenge of the North has been overcome. Steadily, almost routinely now, the ore rolls to Sept-Îles. Free men and free economies everywhere have a new resource at their command, a new strength to draw on. Sailing out from Sept-Îles on every tide, deep-laden ships carry the news of the promise fulfilled and reward earned by all the bitter years of struggle up the line. The reward of iron ore from the North.
Formation of the Labrador Mining and Exploration Company. They obtained a concession from the government of Newfoundland for mineral and power rights in an area of 20,000. Later, control of the company was obtained by Hollinger Consolidated Gold Mines. And in 1942, the M.A. Hanna Company of Cleveland joined forces with the Hollinger interests under the leadership of Jules R. Timmons of Hollinger and George M. Humphrey of Hanna. Ore in the Carroll area is mined by the open pit method, as it is in our mines at Shefferville. However, unlike the ore in Shefferville, which is direct shipping, the Labrador product is a coarse-grained specular hematite running about 37% iron and 42% silica.
This map of the Carroll project shows in red all ore bodies within the Iron Ore Company concession area. Mining is carried out in the Smallwood and Humphrey ore bodies. These two alone have an estimated reserve of about 2 billion long tons of iron ore. The mine is joined to the concentrator by a 6-mile automatic railway. To carry ore from the new project, it was necessary to construct another 42 miles of railway between mile 224 of the Quebec North Shore and Labrador Railway and the new project.
Work on this railway began in May 1959, and in June 1960, little more than a year later, the first passenger train traveled the new Northern Land Railway. From then on, we were able to take full advantage of the 42-mile railway to carry heavy equipment to the site of the Carroll operation.
Blast holes are drilled in each 45-foot bench. The holes are made about 50 foot deep to break to an even pit floor. Drill holes are loaded with explosive and blasted. 10 cubic yard electric shovels load ore into a fleet of 100-ton haulage trucks.
Most of the drilling is done with tricone rotary bits, which chip the rock to break it. Research was done on the bits themselves, and the results of this work helped considerably, not only in increasing the efficiency of the drills, but in prolonging the life of the drill bits as well. However, the rock in the Carroll area is exceptionally hard in places, and it is then more economical to use jet-piercing drills. These drills use oxygen produced in our own plant and fuel oil to produce a very high temperature flame. Water is then used to cool the burner and to produce thermal shock in the heated rock. The flame shatters or spalls the rock by thermal shock and its supersonic velocity. The black diamonds show a nozzle velocity of about Mach 5. This phenomenon is a shock wave which develops in the gas at speeds exceeding the speed of sound. Jet piercing is more or less a streamlined adaptation of methods used in the very early days of mining. Miners of ancient days made fire in the rock to heat it, then poured cold water on it to shatter it. The steam carries the cuttings from the hole. The drill our engineering department and laid out in the field showing depth, spacing, and burden. Intensive records kept of every blast make it possible for the engineers to hold a very close control over future blasts. At the same time, we also are developing new blasting materials. Before the primer is lowered into the blast hole, it is necessary to pump out any water which may have accumulated in the hole. After the primer is lowered into the hole, the slurry is pumped in from a special explosives truck. The explosive is detonated by special primers in each hole and instantaneous fuse which detonates at 4 miles per second. The roads are blocked as the delays are tied in. The rows of holes are detonated in a special order by tying in 15 millisecond delays into the trunk line.
Fire.
This was just a medium-sized blast, breaking about 500,000 tons of ore. The blast over, the area is cleaned up, and the equipment moves in to begin loading. This loading averages about 60,000 tons a day, every day in the year. $60,000 tons a day, whatever the temperature. And 60,000 tons, 24 hours of every day. The huge buckets of these electric shovels are capable of lifting 10 cubic yards of iron ore with every bite. They are the largest in Canada, and it was necessary for us to develop special techniques to train the operators. This 1/12 scale model is used in this special training. The model is exact and is designed to respond accurately to normal shovel controls used by the trainee. dumps are used for stripping waste rock, but specially designed 100-ton trailer trucks are used for hauling ore. The trailer trucks are side dumped. Routine maintenance is done in a service garage near the mine. Major repairs are carried out in the main shops near the concentrator within the industrial complex. Here, the transmission is removed from under a haulage truck. It will be taken to the component shop for repair. Here, another mechanic is repairing a front axle. And a tractor transmission. Whenever possible, components are bench tested. Here we see a steering booster being tested before going to storage. A truck engine is removed from storage, ready for use. Components are always kept ready for use and can be replaced as vehicles are needed, so that equipment gets back into operation with a minimum of delay. Once the 100-ton trailer truck is loaded with ore, its destination is the loading pocket.
Trucks in the mine are side dumped into the loading pocket. The ore is fed from the bottom of the pocket by pan feeder into an automatic train.
The massive 100-ton truck moves into the pocket to be side dumped. Dumping is done semi-automatically on a signal from the driver. A hook is attached to the truck, and while that hook is connected, a bell so that the driver is warned the hook is still attached. He does not drive away until the bell stops ringing. This is the first fully automatic train operation in the world, and no crew is necessary on any of the 4 trains which operate from the mine to the crusher. Train movements are controlled from a central computer near the crusher, and signals are transmitted through the rails to an inductive receiver at the front and rear of each train.
Cars are side dumped directly into the 60 by 89-inch gyratory crusher. Crushed ore then drops to a 50-inch primary conveyor.
The Iron Ore Company's gyratory crusher was the biggest ever to be made in Canada. This crusher will reduce each 100-ton carload to -6 inches in as little as 28 seconds. Armored glass windows provide the operator with an unobstructed view of the car dumping and the crusher throat. The crushed ore is fed by the primary conveyor to storage.
The 60-inch primary conveyor feeds ore onto the 72-inch tripper conveyor and carries it to the ore storage building. Each grinding mill is fed by 3 pan feeders and its own feed conveyor.
This building stores about 16 hours of crushed ore.
Ore is fed into the 21-foot diameter mills where it is ground by autogenous action. Air blown through the mill removes the dry ground product, which is carried to the vertical classifier. The air velocity is reduced and some of the coarse ground product drops out. The air continues to the baffle separator, where more coarse ground product drops out. The airflow continues to two cyclones, which remove fine ground product. The air returns through the main fan to heaters for drying and recirculates to the mill.
Ore is conveyed to the grinding mills from the crusher via the storage building conveyors. The ore grinds itself in the tumbling action of the mill. The mill liners are changed regularly as they become worn. As part of the same regular preventative maintenance program, an electrician is reconnecting a main fan motor after inspection.
Coarse ground product from the vertical classifier and baffle separators is screened at 14 mesh. Oversize is returned to the mill. Undersize goes to storage. Some air is removed from the circuit after it has passed the main fan. It is cleaned in wet scrubbers and exhausted to atmosphere to create a negative pressure in the system.
The screens are enclosed to minimize dust in the mill. The air exhausted to atmosphere is cleaned in wet scrubbers to remove most of the dust.
The coarse ground product from the vertical classifier and baffle separator is now conveyed and distributed by tripper to coarse ore storage bins. The fine product from cyclones is carried by air slides to a fine ore storage bin. The products are taken from the bins by individual conveyors to pulping boxes where water is added.
And so the ground ore leaves the grinding section of the concentrator by conveyor to the process section. All the equipment and functions pertaining to this part of the concentrator are operated and controlled from a central grinding and classification control room. Because of the size, complexity, and fast response required to operate such a system efficiently, automatic controls and instrumentation are extensively used.
Water is added to the ground ore in the pulping boxes, and the pulp is pumped from collector to distributor boxes. The ground ore, still running 37% iron, is distributed to rougher spirals where the action of gravity and centrifugal force separate the ore from waste. Rougher spirals produce a low specific gravity tailings which goes for further processing. A middling fraction is returned in closed circuit, while the first stage concentrate produced is collected and pumped to the cleaner spirals. These spirals produce a middling fraction which is partially dewatered and returned in closed circuit, and a second stage concentrate. This second stage concentrate passes to recleaner spirals, which also produce a middling fraction to be returned in closed circuit, and a final concentrate running about 66% iron, which is dewatered in horizontal filters before going to the pellet plant.
The pumps are controlled from the control room and feed the pulp to spirals. Fresh water is pumped to the mills at 25,000 gallons per minute, and most of it is reclaimed. Approximately 82,000 gallons per minute are in constant circulation. In the Humphreys spiral process, ground ore mixed with large quantities of water is allowed to flow through the spirals. The resulting centrifugal force combined with the buoyant effect of the water act to separate ore and tailings. Gravity and centrifugal force cause the lighter waste products to flow here, the concentrate to flow here, and wash water to aid the section. Products are collected by a series of collector pipes, and the concentrate is dried in horizontal filters. From the filter discharge, the concentrate is conveyed to the pellet plant, or direct to load-out area for shipping. The various banks of spirals, collector pipes, and horizontal filters form the process section and is controlled by an operator in a special process control room close by. Regular maintenance keeps the plant in good operating condition. Filter cloths are changed. Maintenance crews are available for arc air cutting, for welding, and for grinding. A comprehensive warehouse and control system simplifies maintenance and repair. At every stage, the process comprehensive sampling. Most of this is automatic, but notices in various locations keep attendance to a regular schedule wherever manual sampling is necessary. Samples are analyzed in the well-equipped laboratory in the mill building.
To review the process so far, this is a typical sample of crude ore from the mine. The individual grains of iron oxides and silica are clearly visible. This material is crushed and ground in the airfall mills to -14 mesh, and this crushed ore sample still runs 37% iron. In the process section, the spirals use the difference in the specific gravity to produce a concentrate running 66% iron. A concentrate which can be shipped as such or can be further improved pellets. And a tailings containing most of the silica waste from the crude ore. The tailings, however, still contain a certain amount of iron ore and are conveyed to the magnetic separation plant for further processing. The tailings, which are partially dewatered in cyclones, pass to copper magnets. Here, all non-magnetic material is rejected as tailings, while magnetic material is passed on for reprocessing. Magnetic feed from the coppers is pumped to rougher magnets. The non-magnetic fraction is rejected as tailings. The magnetic fraction is pumped to a cyclone. Oversize is reground in primary ball mills and returned in closed circuit. Undersize is passed for reprocessing.
These magnetic separators have fixed magnets inside a rotating drum. Magnetic material is picked up on the surface of the drum as it rotates over the magnet. As the drum continues to rotate beyond the magnetic material drops off and is deposited for further processing. The non-magnetic fraction is not picked up and is discharged as waste.
The undersize from the primary regrind circuit is pumped to a secondary classifying cyclone. Oversize is reground in a secondary ball mill operating in closed circuit, while undersize passes through a DC magnet, causing the very fine particles to agglomerate. It is then passed to a thickener.
In the mill bay of the magnetic separation plant are two primary ball mills and a secondary ball mill. All three are of conventional design.
Feed from the secondary mill is thickened. Overflow water is discharged, and underflow is pumped to finisher magnets. Non-magnetic waste is discharged, and the magnetic concentrate is pumped to the pellet plant.
Final tailings are disposed of in a specially designated area in Wabush Lake. To supply power for the mines and installations of the new mining area, A hydroelectric power plant was constructed at Twin Falls on the unknown river, only a few miles from Churchill Falls. This was the second hydroelectric plant we had developed in Labrador. The first was at Menahek and was constructed to furnish power for our first mining area at Shefferville. Twin Falls is about 110 miles from the mines of the Carroll operation, and power is transmitted at 230,000 volts for distribution at local substations. Our engineers cooperate closely in the planning of mining areas, the construction of roads and buildings, the best use of equipment, and the distribution of operating personnel.
How much stripping yardage is involved in this section, Bill?
Probably about 100,000 yards.
The pellet plant, where the concentrate is processed into pellets, is built close to the concentrator. It is from the concentrator that the pellet plant gets its feed.
The feed from the concentrator is weighed and distributed by tripper to storage silos in the pellet plant. Ore is fed from the bottom of each silo by table feeder and conveyed to the mill pulping box. Water is added and the ore reground in ball mills. The discharge is pumped to a classifying cyclone. Oversize is returned to the mill and undersize to thickeners.
In the regrind area of the pellet plant, the ore is reground to the best particle size for the formation of pellets. The table feeders under the huge 1,200-ton capacity silos provide a constant feed to the regrind ball mills. It travels from the feeders by conveyors at 100 tons an hour. The regrind ball mills are charged with steel balls which grind the concentrate particles to the final required size.
Undersize from the regrind cyclones is passed to the thickeners. Product from the magnetic separation plant is weighed and added to the thickeners. Underflow is pumped to the balling section.
The huge pond-like thickeners are situated outside the building, but the water is kept at a high enough temperature to prevent freezing in winter.
The underflow is pumped to disc filters, where moisture is reduced to about 9%. The ore is stored and fed by table feeder to conveyor. Ground bentonite, used as a binding agent, is stored in a hopper and fed in controlled quantities. The components are mixed in a PK mixer, weighed and fed to the balling drum. Discharge is screened at 3/8 of an inch. Undersize is recycled and oversize goes to the green ball product conveyor. 4 drums feed one conveyor.
The balling section of the plant requires very close process control to form balls known as green balls. Vertical disc filters remove the moisture by suction before the product is mixed with bentonite. As the filters revolve, a vacuum sucks water from the solids. At the discharge point, low-pressure air snaps both sides of the section outward, and the filter cake drops into the storage bins below. Particle surface area, moisture, and percentage of bentonite are critical to the production of balls. The mixture of ground concentrate and bentonite is fed into the balling drums by conveyor. The green balls are produced by tumbling action. The drums are open and slope gently downwards, having a split spiral at the discharge end, which spreads the green pellets onto a vibrating screen. Undersized material goes through the screen and back to the drums again. The balls are tested for mechanical strength by attendants who do a drop test, recording the number of drops before breakage. It is the close process control that ensures the production of even balls of optimum strength and firmness. At this point, the green balls are quite soft and plastic. The whole of the pelletizing process is controlled from this room. Banks of instruments are replaceable in units, so there is minimum delay whenever trouble occurs. The 100-foot-long control room has controls governing every stage of the pelletizing process ranged along the facing sides. Diagrams of these various stages are shown over each set of controls. The kind of work required in the vast mass of complicated controls for the plants, the electricians and other tradesmen have to be given special training to enable them to work efficiently.
The light becomes brighter and the amplitude of the signal is magnified.
Handling at this stage is important to minimize breakage.
The green balls are conveyed to an oscillating conveyor, which spreads them on a roller conveyor. This acts as a screen to remove fines before the balls are loaded onto the pallets in the induration machine.
Fired balls are used as a protective layer both on the sides of the pallet and under the green balls.
The green balls are passed through first and second stage drying to remove all moisture. Then to pre-firing and firing zones where the temperature reaches 2400 degrees Fahrenheit. Cooling in the after firing and 2 zones of cooling is done slowly to avoid breakage of pellets.
Temperature reaches 2400 degrees Fahrenheit, and attendants check the flame through small observation holes. For this inspection, the attendant uses special smoke glass to view the flame. The indurating machines are giant grates for firing the green balls, and the heating is obtained from a series of oil-fired burners on each side of the machine. In some areas of indurating machine checking and maintenance, asbestos suits are worn. The fired pellets are cooled before they are discharged onto a vibrating screen.
The hard pellets from the induration machine are screened. Chips and fines are returned to regrind. A portion is taken as half-layer protection in the furnace. The remainder goes to loadout. In an emergency, the product can be loaded into an emergency bin for direct loading of trains or emergency stockpile. Normally, the pellets go to the main stockpile. Fired pellets are stockpiled by an automatic boom stacker. The pellets are recovered by a series of Mexican feeders under the pile and conveyed to loadout.
The pellet stockpile may contain enough of these high-grade pellets of iron ore to fill several ships. And whether loading is done from the stockpile or from direct loading when the stockpile is low, the supply to the ore carriers is made as required.
The loadout conveyor feeds a surge hopper, which loads pellets into the ore cars for transportation to the port of Setil.
The hoppers are situated right over the railway track, and from them, pellets still steaming are loaded into ore cars. Pellets such as these are the most preferred feed for the great steel furnaces. Four locomotives pull the train of concentrates and pellets. Each car carries over 95 tons of high-grade ore, and 125 cars make up a train. The Iron Ore Company was the first to ship iron. Operation has now added its valuable quota of concentrates and pellets. And so, another train containing over 10,000 tons of high-grade concentrates and pellets goes down the line to Setil. And from the port of Setil, 3 kinds of iron ore are shipped to the steel furnaces. The Iron Ore Company is unique in its operation, able to supply direct shipping ores, concentrate, or high-quality pellets as needed by the steelmakers of the world.
The Iron Ore Company of Canada presents Carroll Mining and Concentrating Operations.